Thank you very much, Anton. So first, well, it's a great honor to be invited to this conference. Of course, Maxime has had a huge influence on everything I know, everything I understand since I started to think about mathematics. I remember in my first year in graduate school, my advisor told me that I should read all of Maxime's papers. This was not easy. Ian Gornowski. So this took me the next several years, but somehow this is how I learned everything about homological algebra and operoids and the BV formalism and Chern-Simons theory and mere symmetry and A-infinity algebras and the moduli of curves and all this stuff. So I think Maxime's this great paper from 1994 in the European Congress of Mathematics, and I spent an incredible amount of time reading this paper. It was great. But anyway, so today I want to talk about something that's long been a dream of mine. So, which is something about understanding some piece of string theory in mathematics. So one of the string theories physicists like to consider is 2B superstring theory, which is something defined in 10 dimensions. And then one of the important ingredients in 2B superstring theory is ADS CFT correspondence, which conjectures some relationship between open strings and closed strings. So what I want the aim of this talk is, firstly, kind of understand a small piece of 2B superstring theory. So it's going to be some twisted form. And this is, something which is maybe familiar to many people, at least some aspects of this, since Witten's work in the 1980s. For example, Witten tried to study n equals 2 supersymmetric gauge theories, and he argued that we're going to understand a piece of that n equals 2 supersymmetric gauge theory by thinking about Donaldson theory. And that was an incredibly fruitful idea. So I want to apply something similar to string theory and supergravity, and also kind of prove a very weak form. So some of the version of ADS-CFT I'm able to access is not incredibly powerful, but it hints that there are more interesting non-perturbative results, which you can see by thinking about this method, which I hope, should be interesting. Okay, so what's the basic idea of ADS-CFT? Firstly, wow, that's weird. What's it?
No, it feels just kind of unstable, yeah. Wow.
Yes.
But the rest is okay.
Some kind of gravity is gone. Supergravity, yes. So remember just some kind of basic story of string theory. Closed strings in type 2B become in some limit 2B supergravity. If we have, if we're on on X, for example, a 10 manifold, and I have Y inside of X, which is even dimensional, on Y, I can consider open strings ending on Y. And this becomes some kind of supersymmetric gauge theory on Y. Okay, this is the kind of very basic string theory thing. And very many, possibly all, supersymmetric gauge theories can be realized in this way, in even dimensions. So I want to talk about twisting this story. And when we twist this story, we're going to get something which is more accessible and more familiar to mathematicians, at least conjecturally. So the first thing to talk about is twisting supersymmetric gauge theory. So just say on R4, say Rn. You have a supersymmetric gauge theory. On Rn, then it's acted on. By definition, this is what it means to be supersymmetric, by some kind of a super Lie algebra. If we choose some Q, there's an odd symmetry, which satisfies Q squared equals 0, then the twisted theory as in Sergei's talk, is equal to the Q cohomology of the original theory. So I'll give you a better definition in a second, because you might ask, what does it mean? What does this really mean? Better. Well, field theories, if you're like me and you like things like the BRST and BV method of considering field theories, then everything in your field theory is a homological object anyway. So for example, the Hilbert space of the theory is a cochain complex. H with some differential of BRST. And the twisted theory with some kind of new complex. That's Q. So we just add on this Q to the differential. And this makes sense because the fact this was a symmetry means that these guys commute. And this, because Q squared to 0, this still squares to 0. Okay, so notice that there's going to be a spectral sequence relating this guy to this guy. That's how they're related. So this is something you can compute. Let's see. This may seem like, the way I've written it down, the procedure is a little abstract, but it's something you can really sit down and compute at the classical level by messing around with various forms of various types and spinors and seeing various maps between them. So let's see what it means for supergravity. And I could be wrong, but as far as I know, this has not appeared in the literature. And this is a bit more abstruse, maybe. Let's consider kind of, say, supergravity on R10. Now, the difference between supergravity and ordinary supersymmetric field theories is that here, the supersymmetry is gauged. That means the fields here might be a metric in a bunch of spinors. And the gauge symmetry is the ordinary diffeomorphisms plus also some fermionic symmetries. Whereas here it's just a symmetry. We're not quotienting by it. So here, supersymmetry is gauged. Now, one way to model this gauging by some symmetry algebra is that is to introduce ghosts as introduced by Feynman and BRST. So that the supersymmetry algebra sorry, this may be a bit abstruse for non-physicists, but there's a math way to say it too, but maybe I won't have time to do it. Now, the way the ghosts work, what ghosts do, it's a way of modeling the quotient by something, because it introduces some Chevalier-Algebran complex based on the symmetry algebra. So the way it works is that if I have an ordinary bosonic symmetry, then the ghost is some odd field. But if I have a fermionic symmetry, then the ghost is bosonic. So fermionic symmetries, symmetry Q becomes some kind of bosonic ghost. Then twisted supergravity is by definition supergravity in a background where Q is constant. So note that this makes sense if Q squared is 0, and so Q preserves something like the background metric. Okay, so I hope this wasn't too confusing to the mathematicians.
Is this just the vector field?
Yes, it's a vector field.
So it's always q squared equals 0.
No, because it's an odd vector field. Think about the de Rham differential. That's a derivation of the de Rham algebra.
So, by constant, do you mean like a killing spinner, or?
Yes. Okay, I said an or 10.
Yeah. Oh.
But if I did in some other manifold, it would be a killing covariant constant.
Okay.
Yes. So the fact that it's killing spinner, that means it preserves the metric. Okay, any other questions?
What do you mean by background?
We're doing like perturbative supergravity, perturbing around this background.
Now, what does it mean? It's a metric?
So there's a bunch of fields, so I'm saying we're going to perturb around some supergravity background where all of the fields are 0 except for the metric and this field.
And this field is a ghost for Fermi.
Yes. And if you think about it, the reason this is a good thing to do is that if I could couple supergravity to some other field theory, and then I put the other field theory in this supergravity background, that would do what we've said above. So that's why it's a reasonable thing. Okay, so now we have some cases of the physics, and hopefully we're going to get to more mathy things in a minute. So the conjecture is that the twist in this sense of the B model of 2B string theory say on, for example, X, which is some Calabi-Yau fivefold. Sorry, X could be or 10, for example. And the reason you want it to be Calabi-Yau is what Ezra said, because that guarantees there to be a covariant constant spinner, is the B model. So what do I mean more precisely? Oh. So the B model will come from open strings. Like the gauge theory will come from open string B models and B branes. So now so I'll explain that in a second. What was it? There are, yes, there are. I wasn't sure if people can see them though. because of the angle. Can people see these blackboards? Yes. Yes. Okay. Well, okay.
Can you resolve the kappa symmetry?
The which symmetry?
Kappa symmetry.
Which is the kappa symmetry?
It's a covariant version of string theory, Green-Shot within string theory.
Oh, yeah. So I don't know how to do this. I don't know how to do this from the worldsheet point of view. I'm only knowing how to do this from the supergravity point of view and the gauge theory point of view. The reason is that from the worldsheet point of view, the space-time supersymmetry is kind of not obvious, and I don't understand. I mean, this is how you should prove it, right? Just I understand space-time supersymmetry from the worldsheet point of view and just calculate, but I don't understand that.
So why is it legal to replace string theory with supergravity? Supergravity is only an approximation.
Right, you're absolutely right. This is only approximations. This is. I mean, you got to hope that there's some better version of twisted string theory, which I don't understand at the moment. But you're absolutely right. This is a twisted form of this approximation to string theory.
Because the usual form is not about supergravity or gauge, it's about string theory.
Yes.
Place one side with supergravity. Why should it hold on the node?
Well, it does hold somehow. I suspect the reason it's going to hold is that you could further guess that the twist of the actual 2B string is the B model string, and the B model string has no instantons, so therefore the supergravity representation is a very good one. Okay, so the B model again is two pieces. It's the open string. If again, like X is some Calabi-Yau, say fivefold, and Y inside of X is a complex manifold, I can do the kind of holomorphic Chern-Simons type field theory, which you get from thinking about the open string gauge theory, which has fields Orhom OY tensor GLN, the shift of 1. It's a sheaf on, it's a coherent sheaf on X.
How do you define holomorphic experiments?
Debug.
You use a double.
It's just with the bundles.
You resolve it as a perfect complex. You take a causal resolution of this guy. So for example, if like X is equal to vector spec V, a vector bundle on Y, and Y is equal to the 0 section, in this case, you can compute the Orhom by a causal resolution, and then the fields are the Dolbeau complex of Y with coefficients Is this make you happier, Jan?
Not happy, but okay, go.
Yeah, I mean, all examples will be of this nature anyway, that I care about. Okay, so you can ask, just as a check of the conjecture, you can ask.
Sorry, do you mean we shouldn't care about other examples, or we haven't got to them yet?
Other examples are interesting, although if you want to construct things at the quantum level, it's much easier to do this kind of example. And to relate to actual supersymmetric gauge theories, that's much, much easier to do these computations on flat space.
What is this conjecture? Can you formulate more precisely what you mean by this conjecture?
So the conjecture is two parts. Firstly, that the twist of type 2B supergravity is BCOV theory. The second part is that if I take, for example, a holomorphic flat submanifold of R10, a linear submanifold of C5, then I can twist the type type 2B D-brane gauge theory in the usual sense, and what I get is this kind of holomorphic Chern-Simons theory. That you can actually calculate, and it's true. Okay, so in the case of, say, y is equal to C2 inside of C5, you expect from the physics, this conjecture should say that this field theory tensor GLN is a twist of n equals 4 Yang-Mills. This you can calculate explicitly, and this is true. I wrote a paper calculating this several years ago, kind of about 2011, and there are many other examples where it really is correct. So,
Which square C-cube we pick? The dilutional, yeah.
Probably C2.
I'm sorry, could you repeat your answer to Anton's question?
So in what sense is this a precise conjecture? Yes, so there are two parts. So the first conjecture is that the twist in the sense of type 2B supergravity, just at the classical level for now, is BCOV theory. And what's BCOV? Because BCOV theory is what you get by the supergravity theory associated to the B model. So I was about to say that in a minute.
BCOV theory
On X, on a Calabi-Yau fivefold. I was going to say that in more detail in a second. And then the open string version is that, so here, if we, so more generally, so the open string version is that the twist of the D-brane supersymmetric gauge theory is this kind of holomorphic Chern-Simons based on this kind of gadget.
But where in the CFT we're comparing closed string and open string.
Yes.
I don't see it here, so yeah, rather close and open over.
Right. But so what we're saying is, okay, the kind of diagram I want is like open, kind of closed, ADS CFT, and then there's the B model. We have open, closed. I was about to say in a minute what the closed B model is, but this is going to be some kind of holomorphic Chern-Simons, kind of BCOV. This is twisting. This is twisting. And here, ADS CFT. And then this is, I'm able to kind of prove some shadow of this statement. I haven't talked about this yet. Okay, so we expect again that the B model closed string, for example, on X, a Calabi-Yau fivefold should be equal to a twist of 2B supergravity. This is the conjecture. So let's see if I can make this. I need to explain to you. So when I'll talk about ADS-CFT in this B twist, we first need to understand what the closed string B model is. Oh man, that's really silly. I pulled out the same blackboard I just pushed up. So I need to explain to you what the B model closed string theory looks like. So fields of species of E theory, well, you can write them in two ways. It's going to be the cyclic cochain complex of the category of perfect complexes on X. And then you can use the Hochschild-Kosten-Rosenberg theorem to write this more explicitly as polyvector fields on X adjoin some parameter t with some differential plus t del. This is the usual d-bar operator, so I just need to explain briefly. Polyvector fields on X is the Dolbeault complex on X with coefficients in the exterior algebra of the tangent bundle, and the del operator is a divergence operator, corresponds to the con-B operator, and it maps omega I x wedge j t to wedge j minus 1 t of x.
So it's obtained from the Durand.
Yes, exactly, yes. Okay. Sorry. This is isomorphic to omega 0 I x wedge 5 minus j t star of x. And here it's the usual Durand operator.
For instance, one should speak about some non-compact X, but yeah, let's space, yeah.
Yes, exactly. But this correspondence is going to work on some non-compact X. Well, since I've erased this already, I will use this blackboard. So the questions we want to address are the following.
Or can you define more precisely? Okay, these are the fields of this.
Yes.
This zero level. So is it a class coupled with their path integral?
Yes, it's the way we're going to treat it is it's a field theory. So it's a field theory in the BV formalism. So it's going to be described by a shifted Poisson manifold. Like in when Tony's going to talk about this kind of thing. However, this is a kind of degenerate theory. Normally it's described by a symplectic manifold. This example is not symplectic, but Poisson. So I need to describe you what the DG manifold structure is and what the Poisson bivector is. So the DG manifold as I learned, if you remember reading Maxime's papers from the early 90s, DG manifolds, the differential is given by, corresponds to some Lie bracket on some space. So it's controlled by the differential graded Lie algebra. It's a kind of formal. Differential graded Lie algebra, which is polyvector fields on X, T, shifted by 1 with the Schouten bracket. Are you happy with this? This kind of formalism, Anton? Or? Oh. So to give a DG manifold, I need to give you it's the spectrum of a DG ring. Got a formal DG manifold. So the ring of functions are cochains Chevalier-Almer cochain complex. So really, the DG manifold is equal to some kind of formal extended moduli space of deformations of X. And you can also think of it as the moduli of deformations of category of perfect complexes on X as a Clavier category. Degree T is equal to 2, yes. Exactly, yeah. Oh, when I say something like this is the content of Maxime's famous theorem about formality. This equality is this kind of very hard theorem. Kind of formality theorem. Okay, well, what's the Poisson structure? So the Poisson structure, Poisson kernel is, let me just finish this sentence, sorry. I take the delta function on the diagonal, apply this delta operator, that's the Poisson kernel. So, sorry, Ezra.
Don't you want to shift down by 1, not up by 1?
You want vector fields to be in degree 0. Oh, yeah, yes.
Okay.
Yes, absolutely. Sorry about that.
This is classical field theory?
Yes, and the quantum field theory, I will explain in a minute that you can quantize it.
Yeah, that's not very obvious.
It's extremely non-obvious.
So the theory is about threefold, and you're doing fivefold.
Yes, and it's also, if you think about it, it's a non-normalizable. So, but there's,
It was already in the threefold.
already in the threefold case, yes, but, so that was actually the next topic I wanted to explain, is when can you quantize this and what does it mean?
So these are CFT solid vector fields?
Yes. So when you take cochains, it's a topological vector space. Okay, so when can you quantize? And what does this mean? So firstly, for the closed string, C of V, the answer is that you can always quantize. So why would you expect this? So I'll suggest two different ways to think about it. So one is, one way, you can think about topological field theory. Topological field theory in the sense of Maxime, I did some work myself. This produces for you something based on a Clavier category. Yeah, so that's why it's not really going to be good enough for what we want to do. I suppose you could always think about compactly supported sheaves, but I think it's still not going to be really strong enough for what we want. Well, the second point of view on this, so my collaborator and myself showed how to do some quantization in perturbation theory.
Some choices like splitting or quantization.
No, but if you want to get this, the kind of thing we want to, that choice does not appear for what I mean by quantization, because
You mean summation of a generator? Yeah.
you want some solution of the master equation. The master equation you don't need to extend to the boundary of the Mumford space. Okay, so maybe I'll say a little bit about our argument in a second, because our argument, kind of similar to the TFT argument Maxime introduced, involves the open-closed theory. So fix a sheaf, say E on X. Can we quantize the couple theory for like the couple open closed theory? And the answer is if and only if the total Chern class of E is 0 in cohomology of X. So what's
Does this have to do with constant ambiguities in Chern-Simons theory? Or?
Yes, and it has to do with something in the A model, which you're very, very familiar with, I'm sure. If you want to kind of count curves with boundary on some Lagrangian, then in this count there's a codimension 1 boundary when the circle shrinks to a point. So there's this argument of Dominic Joyce that says if this is the boundary of some chain, then you can cancel this anomaly by thinking about some kind of closed strings. So it's exactly that kind of thing.
So in that case, you get the one higher dimensional homology space gives you some space of choices of quantizations, and you have the analogous thing here.
Yes. Yes, but if you work in but if you take something which is a kind of canonical trivialization, so for example, the structure sheaf plus the structure sheaf with a shift, then it's completely canonical. So for the structure sheaf on X plus OX of 1, there's a canonical quantization of the open-closed theory. And why is this? Well, the argument C and I have, it's kind of a pretty argument, but I don't have time to explain in any details. Given I have 15 minutes left, is that right? Yeah. So I'm having to say something about AD or CFT. So there's some kind of cancellation between kind of cohomology groups controlling ambiguities of quantization. For the open theory and the closed theories. Okay, and the final thing you want to ask is, when can we decouple the open theory? From the TFT picture, this comes from a kind of codimension one boundaries, like Maxime kind of mentioned a minute ago. I have some surface like this, and I might have some cycle. There I might have some cycle which shrinks. And as Maxime said, the issue here is, in the A model, this is not a problem, but in the B model, it involves a choice of trivialization of the Hodge filtration. And you kind of don't want to choose a trivialization of the Hodge filtration in general, because that's not something you can do locally on a manifold. It's kind of a global thing. So the answer is, you can do this. This isn't in the following situation. So Y is an even dimensional Clavier. E is a sheaf on Y. I take Y inside of, say, Y cross 0 inside of Y cross C, and then we consider the kind of the theory on Y cross C with the sheaf I star V.
What does it mean?
Well, so if you think about these moduli, we're going to have some solution of the master equation coming from the moduli space, integrating over top chain to the moduli spaces. And the boundary of the moduli space, that corresponds to various terms in the master equation. So if you want to have a solution of the master equation just for the open string piece, you want to arrange so that the boundary of the moduli space only knows about kind of open string degenerations, so not this kind of one. Okay, so I think 10 minutes left. So I think I'm not going to get to explain much about ADS CFT, so I just have to briefly explain what kind of thing we find when we quantize. And then a little bit about ADS CFT. What does quantization give us? Firstly, the closed string. If I take some kind of open subset of X, we have this sheaf of Lie algebras. I can take Chevalier algebra cochains of this guy. And we think of this as classical observables. So quantization produces some cochain complex. Which looks like the same kind of thing, but with a h-bar dependent differential. So the h-bar dependent differential comes from things about higher genus surfaces. And, well, it turns out here we had a commutative algebra. This h-bar dependent differential with the BV formalism is no longer a commutative product. But we have product maps. If I have U and V which are disjoint, in W, we have a product map like this. product map. So this means we have what I call a factorization algebra. So how should you think of this? I'm sorry that I have to. I'm writing like a book which is like 500 pages long with one of my collaborators on this kind of factorization algebras. So I'm sorry I said everything about it in like half of a blackboard. But the picture is very similar to Graham's picture for what a quantum field theory does. We should think, for example, if U, V, and W are disks, that the product comes from a cobordism. So that these spaces we assign to U and V, they're like the Hilbert space of the theory on the boundary of the disk. This product map is the cobordism. So it's the kind of thing people are kind of familiar with. Okay, any questions about this? I've probably lost everybody, but that's. So I wanted to get there will be a punchline in about a minute. So similarly, open string. Kind of similar. If I have some sheaf on X, which is supported on some Y inside of X, then I can send U kind of this cochains H bar the sheaf Orham, cochains of the sheaf Orham, with some quantized, some differential which depends on H bar. And think about what is the differential? The leading term will be D bar. Kind of heuristically, it has pieces which come from counting curves. Like the A model analog will have pieces coming from counting curves. Has a term from the pairing, it's the BV operator, plus some kind of sum. Okay, does this make sense? I mean, just for people who like topological field theory, I know Kenji's thought about something very similar. All that's going on is if you think about these kind of, in the A model, if you think about counts of curves landing on a Lagrangian, there's some master equation. That master equation tells you some differential squared is 0. That's this differential. Okay, so in the 5 minutes, I want to explain how these things are supposed to be related. So I'll explain how they're related in a simple example. The example I'm going to consider about is on C3, what I make, which is made non-commutative. And I put on we have a polyvector field which is dz1, which dz2, so that the Poisson bracket is that z1, z2 is 1. The first two coordinates fail to commute. And that we have inside of this guy, I have c for the first coordinate, inside of C3. And my sheaf is the structure sheaf on C, kind of tensor Cn plus Cn1. C, the first copy of C, inside of C3.
This is coisotropic?
So, yes. No, it's we should really think of it as something symplectic cross C. So it's Lagrangian in the symplectic guy.
Okay, so you can quantize it.
So we can quantize it exactly. Now, if you think about what do you find kind of the ORHOM in this non-commutative world, well, for the first copy of C2, we know how to compute ORHOMs into something non-commutative. We're just going to get like the RAM complex of C, and then I join an odd parameter from the ORHOMs in the other guy, so that the fields look like C epsilon tensor GL n/n. So if you think about this, this is like the B model for the classifying space of GL n/n. Another way to think about it is the topological limit of Yang-Mills, of 2D Yang-Mills. I'm sorry, I don't have more time to explain about this. Okay, so what are the open strings factorization algebra? Well, it's an E2 algebra. Because we're dealing with a topological theory. Topological. The closed strings if you think about what the structure you find, we have a non-commutative C2 cross C. Well, the non-commutativity makes it topological here, whereas the other guy, it's a holomorphic thing. So it's like an E4 vertex algebra. So let's give names for these guys. We have the kind of A open string, and we're going to take some kind of slash n as this n goes to infinity. So we need to take the n to infinity limit, which you can do in this situation. And we have the kind of closed strings, which is the cochains of like polyvector fields. And then the theorem that the open string guy is equal to the causal dual of the closed string guy as an E2 algebra. Sorry, this would have been more of a punchline if I had time to explain it. So, but this is the more general claim is that this is what the duality gives us. Each side we have something like holomorphic version of an EN algebra, and they're causal dual. So I take the closed string guy restricted to the submanifold, and these things are causal dual. So what was I going to say? Oh yeah, so why is this? Kind of if you look at the classical level, this causal duality is simply the Hochschild-Kosten-Rosenberg theorem. Hochschild-Kosten-Rosenberg theorem combined with Segan's theorem about large n, the algebra cohomology. So there at classical level, it's a kind of a triviality. The semi-classical level, there's a Poisson bracket. This turns out to be a very hard theorem. This is Maxime's formality theorem, because we need to look at the Lie algebra structure. Rather, it's the cyclic version of the formality theorem proved by Wilwacker. But at the quantum level, some kind of deformation of this. And from the point of view of physics, what we're seeing is, we're computing the algebra of operators, the OPE of the large n gauge theory in terms of something kind of dual to this in the closed string theory. Okay, so sorry I ran a little bit over, and thank you for your patience.
Questions? This is very nice question. got lost. In this
I'm sorry.
differential, H-bar differential, our terms are kind of polydifferential operators.
Yes.
It's all local.
It's all local. Well, it's a little subtle. I mean, there's some kind of choices, but you can make it as local as you like.
Yeah.
So there's some kind of...
And also in ADS CFT, you get some kind of boundary to infinity, or where is this boundary to infinity?
Yes. So I didn't have time to explain this. So the reason I chose GLN/n for the reason that that means that the fundamental class can be trivialized, with a cycle trivializing it also has support on C. But if I chose GLN, then I would need to trivialize the class of C as a class on C3. And that trivialization is going to be something supported in all of C3, which has poles along this C. So that means, so that's where, I don't fully understand this, but what happens is that I need to remove C, and then I have something which poles on this, on C, and so I get something more familiar from the ADS CFT picture. Make any sense? I mean, I'm still a bit puzzled about this aspect. So, Ezra, yes.
So this is going to be very vague, but I'm trying to understand the meaning of what you said. And if we drop back down to quantum mechanics, E1,
Yes.
then we've got, say, the de Rham complex on one side and differential operators on the other.
Yes.
And somehow the idea of resolution, that the de Rham complex resolves the constant sheaf, is flung by Kossel duality into Morita equivalence or something. Does this make any sense?
It's possible. I mean, I think it's somehow easier. I mean, so we're not saying that the de Rham complex is Kossel dual. It's rather cochains in the de Rham complex. Some deformation of that. So at the classical level, this is the E2 algebra of cochains of GLN/n. And at the classical level here, it's an E2 enveloping algebra. And they're Kossel dual. I mean, it's some E2 enveloping algebra.
Oh, I was simply presenting a kind of a toy model. I wasn't meant to be a special case of what you said.
Yeah.
But then, I mean, somehow, is this like a quantum field theory analog of sheaf theory versus Morita invariance? That's what I was doing.
I don't know. I can't quite parse it in real time. But I see what you're saying. It looks a little similar. But
So classical Kossel duality is mediated by bimodule. So is what's happening here?
yes. That's an interesting question. So another way to say it's mediated by an augmentation is another way to say it. So you need to show why is this augmented and why does that? And somehow if you think about what the augmentation means, you remember we were saying that it's sometimes hard to decouple the open string guy. So the obstruction to augmenting this guy is precisely the obstruction to decoupling them. That's the kind of thing. Another way to say it is if you look at the couple theory, looks like the Hochschild cohomology of the close string guy. Right? And that's what you expect from. Does that answer your question?
No more questions. Let's thank you again.
Thanks, Anton.